Okay. All right. Well, it's great to be here and see you all face to face. And I should, all things go according to plan, I should be here also on Friday. So, I've already had my office hours for the week, but I will probably be here early on Friday. Uh, Happy to stay a little bit late today, and would just love to hear more about you guys, get to know you better. I know it's awkward. You guys are probably sick and tired and to death of remote learning and that type of thing, right? So I did my master's and PhD at University of Central Florida, and we had adopted remote learning back in the 80s when they would send VHS tapes to remote centers, so you could, participate in class from one side of town if you lived and worked on one side of town, so you didn't have to drive all the way over to the other side of town. So, I've been, on that side of remote learning for a long time, but I know it's not ideal. So appreciate you guys hanging with us here. This kind of started last year when I had a professor quit at the last minute, right, like days before the semester started, and so they called me up, and I was just in the process of retiring from my private job and private industry job, and was happy to help out my old colleagues. As you know, I think you know that I used to teach here full time before I moved home, back home to Missouri and all. So, God, come on. Yes. Okay. All right. So let's go ahead and get started. And so today I looked at our schedule and how we're moving through the course, and I think we have an opportunity to discuss receiver equalization and timing synchronization. These are a little bit advanced topics, and we're just going to kind of cover the surface of them. We're not going to get real deep on them, but they're really like a super important aspect of being a professional practicing communications engineer, right? So your ability to do equalization, that's kind of where the art is in communication engineering, and what really makes kind of separates the good systems from the mediocre ones, type of thing, right? So today we'll just briefly review the functions of receiver, look at equalization, just touch on timing recovery, and then we'll talk about the MATLAB assignment. I'll give you kind of some background here. We're getting into the area where this assignment that I just released like half hour ago or something like that, it's going to be something where you're going to run the examples, kind of built-in examples. And you can just sit there and blindly just run them, right? But I want you to explain what's happening. And on the first part, there's going to be some additional work that you're going to do. And we'll start introducing that today and talk a little bit more about that on Friday. And hopefully that can be due next week before we have another little break for the Easter holiday and all. And then we'll start talking about error control coding, and we'll have a unit on that, a MATLAB unit on that. So when we talk about functions of a receiver, we have modulated signals. We run them through an AWGN channel, and then we demodulated the signals, right? And we've converted those back into bits, and we've compared those to the input bits and look at, you know, this is our error rate and that type of thing, right? So, but before spring break, we talked a little bit about intersymbol interference and how band limited channels, or channels that have a non-flat frequency response, can mess with your pulse, right? And then when you have a pulse at one instance of time, it can affect the measurement of the next pulse or the previous pulse, right? And so it becomes difficult to isolate these things in time. They get smeared out in time due to the band limiting aspect of the channels, right? So the equalization helps us to compensate for those, right? We talked about a raised cosine filter and how that can help shape the pulse to begin with, but then we can also equalize some of the effects. We also talked about how, like when we compared the correlation receiver and the match filter receiver, and we said, oh, they're identical at the sampling instant, right? And they're different in between. Remember that was kind of showed up on the test question. But that kind of begs the question of how do we know exactly when to sample it, right? So if the results are the same at that sampling instance, you know, how do we know when that sampling instance is at the receiver, right? So we'll talk very briefly about that. Talk a little bit about, you know, well, we've already kind of talked about these things, symbol detection, right? Estimate the most likely symbol the transmitter sent, and we spent a couple of weeks looking at that, right? With those optimal, maximal, a priori, always have a hard time pronouncing that, the map receiver and the maximum likelihood receiver, right? So, and then there's this, the detailed analysis of these functions is typically covered in the graduate course, meaning that these first two things here. We're going to cover these things on a conceptual level. So here, this is an example from the book. You have a signal coming in here from a transmitter, goes through, well, they call it transmission media here, but we call that a channel, right? And so there's going to be some noise added to it, maybe some distortion. Then when it goes through that, it's going to get attenuated and it's going to have some distortion added to it, right? So we use a preamplifier to boost the signal so that it's minimally affected by the noise. And then we have this equalizer, which we'll talk about today. Then we peel off a little bit of that signal and we extract some timing information. So we know when to sample it. We send that to the sampler and decision, right? So now we sample the signal and we go through that thresholding, look at those decision areas, decision boundaries, and map it to a particular symbol. And then we demodulate that symbol into bits, right? In this case, from the book, the example they're showing is they're actually regenerating this, right? So let's say you've got a transatlantic or trans-Pacific cable that you're sending a signal along. It's not wireless, but it's still a communication system, right? So you have to regenerate that signal as you go because it attenuates way too much, right? And so so in that case, you're regenerating, but in a conventional receiver, we just now interpret those bits as data, as information, right? So in terms of equalization, practical channels introduce attenuation and distortion in the form of dispersion. Okay, what is dispersion? Well, that's where it can be a couple of different things. It can be where your amplitude response of your system is a function of frequency, right? So that's that band limited channel. More complex version of dispersion is when your velocity, your phase velocity of a wave depends a little bit on the frequency, right? So normally we think of the velocity of the wave as maybe the speed of light, c, right? And 300 million meters per second. And we know that that's related to the frequency and the wavelength through c is equal to f times lambda, right? And but that speed, that phase velocity is not always constant in more like practical materials when you're propagating through a wire or a fiber optic or through the atmosphere or something like that, right? So there can be this frequency selective attenuation and frequency selective velocity, right? So simplistically, we can equalize using a filter with the reciprocal response of the channel, meaning that, let's see, I get to write on the board because I'm here. I'm sorry to the people that are watching, will watch from home. But if you have a let's say a channel response that looks like that, right? Then you could equalize it by doing a channel, by doing a compensator that's the reciprocal of that, right? Where maybe the channel attenuates, then we boost it a little bit, right? And where the channel is maximum, maybe we just probably wouldn't attenuate it, but that would be kind of our nominal, and then we boost it where it needs to be. So we could just measure that channel response, take the reciprocal of it, right? 1 divided by that channel response, and then develop a compensator, an equalizer based upon that. Now, what's the problem with that? Okay, so I say simplistically, right? So it kind of begs that there's a problem with that. Well, our signal is in here, right? So we might have some signal that spans this bandwidth of the channel, but we're also going to have noise in there, right? And now if we do this little compensation, then this noise here and here in this trivial example is actually going to get boosted. All right, so we're trying to compensate, but in doing so, we're actually boosting the noise. That's going to degrade our signal to noise ratio, right? And then that's going to make our decision thresholding harder, right? So we went through that analysis, plugging things into the Q function, based upon the tail of the additive white Gaussian noise. And then as we do that, we the greater the noise, the lower the signal, or that lower the signal noise ratio, the worse things get, right?